atomic radii. Let's give a small definition here. It's the distance between the center of the atom to the boundary. And what is the boundary? It's just where the electrons, so this stands for electrons, spend about, give or take, 90% of their time in. Now let's expand on this definition. When we look at an atom, so let's say this is the nucleus in here, we have these little rings, and these rings are pretty much these clouds. Okay, they're not necessarily rings, but they're clouds, give or take, where they are in that specific area, and the electrons move around the atom as a cloud. Okay, and then Schrödinger equation showed that. So there are multiple of these clouds within the atom, and the more clouds there appears, the greater the size of the atom, give or take. We need to understand how the atomic radii can change when electrons get removed or electrons are gained for the atom. Let me show you a specific example. Let's look at magnesium here. And let's look at chlorine. Magnesium has 12 protons, 12 neutrons. Again, 12 protons because its atomic number is 12. 12 neutrons because that is the difference between the atomic mass and the atomic number. Magnesium's atomic mass is 24, 24.3, rounded down to 24. Subtracted by the atomic number of 12 gives you 12 neutrons. We're drawing the cloud here. Again, we don't necessarily know where these electrons are, so I don't really care where you draw these electrons. You could put them north, south, east, west, does not matter. It is kind of impossible to figure out where they exactly are in terms of their position and momentum based on the Heisenberg's uncertainty principle. So be lenient where you draw these electrons. It's really not a big deal. So we've drawn 10 electrons so far. Those are what those dots are. And I drew 2 more over there so that we have 12 electrons. Again, the electron number for an atom is the same as the proton number. So we have 12 electrons drawn. Now let's do the same thing for chlorine. Chlorine, 17 protons, 18 neutrons. I need to draw 17 electrons because we have 17 protons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 7 more. 7. Alright, so we have 17 electrons now. We have to look at something called the shielding effect. How many electrons are shielding the valence electrons on the very last ring? It's a different color here. This here is a valence electron. This here is a valence electron, so there are 2. Same thing here. Valence 1, valence 2, valence 3, valence 4, valence 5, valence 6, and valence 7. These are the electrons that are going to do bonds of formation. different intermolecular forces. The inner electrons over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, these ones act as a barrier. What do I mean by that? The attraction between the positively charged, again it's positively charged because protons are positive, neutrons are neutral, so overall it's positively charged, very dense in there as well. The protons here have an attraction towards the electrons. Now I know we're focusing on the valence electrons here on the very outskirts of the atom. There is this barrier. These 10 inner electrons on the inside are making it very difficult for the valence electrons to attract towards the protons in the middle. It acts as a shield, hence why the name is called the shielding effect. And the shielding effect makes it difficult for something called the effective nuclear charge to occur. Effective nuclear charge. And I'm not going to write a big definition for it, no point, for the sake of time. The effective nuclear charge, I'll just do a small little formula. Okay, ZF just stands for the effective nuclear charge. Z here is the atomic number. So the atomic number. And again, atomic number is the same as the proton number, so this could just be represented as the proton number here. Subtracted by S, with this stands for the shielding constant. So the shielding electrons that we have there in the middle. As you can see, the greater the amount of protons that we will have, also known as the greater number of atomic number, the greater this value will be. It will drive this effective nuclear charge higher as well, right? If this one increases, of course this one is going to increase too. So which one is going to have a stronger effective nuclear charge? Well, let's look at the 10 inner electrons of both. Inner electrons. This one here also has 10 inner electrons, but this one has 7 valence electrons on the very outskirts. This one here only has 2 valence electrons on the very outskirts. So the 10 inner electrons remain constant for both, but the valence electron number is greater in the chlorine. Because it's greater in the chlorine, it's because of a result of there being so many electrons, right? There are 17 electrons, so by nature, naturally, they're going to have more valence electrons on the outskirts. This one only has 12 electrons, so you're going to have a smaller amount of valence electrons. This is why, whenever we look at the effective nuclear charge, again, I know I wrote it as a formula here, but it's pretty much what the electrons feel. The electrons are going to feel a certain amount of positive charge, a pull, okay? Again, only electrons move. Protons do not. So the electrons want to go towards the protons, and it's going to feel some sort of positive charge from that nucleus, the dense center in the middle. The more electrons there are, the greater the effective nuclear charge. Maybe I'll write this here. The greater the number of electrons there are, the greater the effective nuclear charge. Because there are many protons in the middle, right? If there's 17 electrons, there's going to be 17 protons. Strength comes in numbers. I want you to think of it that way. So the more electrons there are and the more protons there are, collectively, holistically, there is a lot of them wanting to get together. So the attraction is very, very powerful. So this is going to be extremely compact. All right, very compact. It's going to squeeze together. Again, strength comes in numbers. Magnesium, 12 protons, 12 electrons, so maybe it's not as compact. Not as compact. And because it's not as compact, it's going to be more full. Maybe I'll write this here. It's going to be more full, more expanded. Okay? This one here, not as full. Not as full. Because there is electrostatic repulsion between the electrons. The electrons here, and 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 the electrons here. There is a lot of repulsion because of the nature of their negative charges. Negatives and negatives do not like each other. So if there is less of the electrons, there is going to be more attraction. Okay? Why is this more full though, if that's the case? Because this one has more electrostatic repulsion because there are greater number of electrons. It honestly all comes back down to the Z value, the atomic number. The greater the number of protons there are, and if there's a lot of electrons as well, okay, let's assume the electrons didn't fly away, or we didn't gain any electrons, just by nature, if we looked at it this way, there would be a strong effective nuclear charge, so it would be very compact. The electrostatic repulsion that we exhibit from the electrons, from all these electrons, does not outweigh this effective nuclear charge. If there's lots of protons that we have here, then there's going to be a very, very compact force. So that would outweigh the electrostatic repulsion. Again, there is electrostatic repulsion everywhere between these two atoms, but it's the number of the atomic number that's higher that is going to make it squeeze together and not expand as much. All right. I want to have you look at a particular question. All right, the question there says, explain the shielding effect. So what is the shielding effect? The shielding effect is when electrons on the inner side of the atom act as a barrier to the valence electrons wanting to attract towards the positive nucleus. That stands for positive. Okay, and how does it affect the size of the atom? Well, the greater the shielding, the less the effective nuclear charge, sorry, the ZF for short. Therefore, again, if there is less effective nuclear charge, it's not going to be as compact, so it's going to be bigger. All right, the atom will be bigger. It kind of goes vice versa, right? Maybe I'll write here as well, vice versa. All right, vice versa means if there is less shielding, so there's not a lot of electrons in the middle that is blocking the valence electrons from the nucleus, this means that the valence electrons are closer to the nucleus, and then they're going to obviously want to get closer because of the attraction, then the atom will be smaller. Okay, so that's number 16. Let's have another look at this question here. List the following elements in order of increasing atomic number and then in order of increasing size. So we have oxygen, we have tin, we have potassium, and we have krypton. Now, all of these have a particular atomic number. Okay, oxygen has an atomic number of 8. Sn has an atomic number of 50. Potassium has an atomic number of 19. And krypton has an atomic number of 36. So if I were to draw this out as so, increasing atomic number, let's have least over here and greatest over here. Oxygen would be here because it has the smallest atomic number. Then we have potassium, then we have krypton, then we have tin. If we look at another angle where we are now looking at the increasing atomic size, let's do the same thing. L stands for least, G stands for greatest, okay? Increasing atomic size. On the periodic table, if it goes towards the bottom and towards the left, this is an increase in atomic radius. So it's just bigger, more full looking, more expanded. Let me take you to the periodic table here. Again, what were the elements in question? It was oxygen, it was tin, it was potassium, and it was krypton. Okay, where is oxygen? Oxygen is over here. Where is tin? Tin is over here. Potassium over here. And krypton over here. What did I say? The increase of atomic radius goes down towards the bottom of the periodic table, down the group, and towards the left of the period. So, naturally, anywhere here would be extremely large. Anywhere here would be extremely small. Oxygen fits that description. So oxygen would be extremely small in its atomic radius. That's quite obvious. Next, this is also quite obvious too. Krypton, not too far away, and it's still kind of in the middle, but still on the right side, so it is still smaller. Now it gets a little bit tricky. Which one is the next? Is it potassium? Oops. The potassium over here, or is it tin? Well, this is going to be quite difficult to really comprehend without a data table. By and large, and naturally, you would want to think that tin is actually larger than potassium. Let me write it here. Let's have a little table here. Again, least, greatest. Oxygen, easy to establish. Krypton, easy to establish. Potassium is what I want you to think of to be the next in line. So it's the second largest, followed by tin being the largest. Why? Because tin has an extra period layer. Potassium here is on the same level as krypton. If you have an extra period, so an extra horizontal line here, extra horizontal row, this means that you're going to have an extra layer of electrons, the cloud that I talked about in the beginning. this creates a shielding effect. The greater the shielding effect, the more repulsion. So because tin here, right, has an extra shielding effect, it's going to expand larger. It's going to get bigger. That's why I have tin listed here. Potassium, I understand it's on the very left side. You're probably wanting to put this at the very, very end, being the greatest in terms of its size of its atomic, regarding its atomic radii. I understand that. But if you're not given a data table, the shielding effect comes first. It outweighs how far left it is. Now, here's where it gets interesting. The atomic radii here, let me show you over here. This is all the atomic radii. And the atomic radii is measured in picometers, just in case you wanted to know the unit. 227 is the atomic radii for potassium, but look at tin. It's only 140. Oh my gosh, what did we do wrong? Didn't I say that the shielding effect takes precedence over how far left that element is? Yes, because we weren't given a data table. If you're not given a data table, you have to use the shielding effect as priority. Where is the fine line of how far left and how far down? We don't know. But this is all based on tests and data, the rigorous design, and we've come up with this number. Because we have a data table in front of us, it seems as if the shielding effect does not outweigh the potassium, just because the tin, not so far left in the transition metal area of the periodic table, but potassium is extremely far left. So because of that fact, this potassium is going to take precedence. Again, because we have this data table. If you were not given this, you would have to assume that because tin has an extra layer, an extra amount of shielding effect, that takes precedence. I'm showing you the data table now because there is exceptions to this rule. This here is an exception. Again, tin, right over here. Potassium, all the way over here. If we had another element, maybe somewhere over here, maybe the shielding effect would outweigh the potassium of being how far left it is, because now we're selecting an element that is closer towards the left side, but also has an extra layer. Or maybe an element here or an element here. Where is the fine line to determine what outweighs what? We don't know. But use the shielding effect as an outweigher, unless you are given the data table. Then you have pretty much the answer in front of you. So, what is our answer over here? Well, we have oxygen first, potassium. Sorry, what am I saying? We had oxygen first, and then I think we had krypton. Yes, so we had krypton. And then, again, we wanted to put potassium first, but no. We need to put tin first because we have the data table. If we did not have a data table, tin would be last. Then potassium. All right. Let's do one more question. Number 18. List at least 3 factors that affect the atomic radius. Well, number 1, we have the shielding effect. Number 2, we have the amount of electrons. Again, shielding effect acts as a barrier towards the positively charged nucleus and the valence electrons on the outside. The amount of electrons also plays a part because sometimes the electrons are going to be acting as electrostatic repulsion to expand the the size of the atom. But if there is a plentiful amount of protons within the nucleus, rather than expand, it's going to want to go towards the nucleus, and it might actually become a lot more compact. Okay, so this is a weird dichotomy that we have to understand. Is the repulsion going to outweigh the effective nuclear charge, the attraction to make it compact? This is where it gets a little bit tricky. This is where I'm going to bring our third point. The charge. These two correlate. The greater the positive charge, or the greater the negative charge, it's going to make us determine what outweighs what. And unfortunately, this is going to be in the next video. Think of this as a cliffhanger.